Hello, everyone. This is the presentation of Group 6 about soil water. Soil water contains nutrients that move into the plant roots when plants take in water. In nutrient management, a proper balance between soil water and soil air is critical since both water and air are required by most processes that releases nutrients into the soil. Soil water is particularly important in nutrient management. Soil water is important for three special reasons. First, the presence of water is essential for all life on Earth, including the lives of plants and organisms in the soil. Water is necessary for the weathering of soil. Areas with high rainfall typically have highly weathered soils. Since soils vary in their degree of weathering, it is expected that soils have been affected by different amounts of water. Soil water is the medium from which all plant nutrients are assimilated by plants. Soil water, sometimes referred to as soil solution, contains dissolved organic and inorganic substances and transports dissolved nutrients such as nitrogen, phosphorus, potassium, calcium to the plant roots for absorption. The amount of water in the soil is dependent upon two factors. First, soil water is intimately related to the climate or the long term precipitation patterns of an area. Secondly, the amount of water in the soil depends upon how much waters a soil may hold. Um, the capillarity. Water molecules have behave in two ways. First is the cohesion force. Because of the cohesion forces, water molecules are attracted to one another. Cohesion causes water droplets. Next is the adhesion force. This force is responsible for the attraction between water and solid surfaces. Water also exhibits a property of surface tension. Water surfaces behave in an unusual way because of cohesion. Since water molecules are more attracted to other water molecules as opposed to air particles, water surfaces behave like expandable films. This phenomenon is what makes it possible for certain insects to walk along water surface. The capillarity, capillary action. It is a combination of cohesion, adhesion, and surface tension forces. It is demonstrated by the upward movement of water through a narrow tube against the force of gravity. It occurs when the adhesive intermolecular forces between a liquid, such as water, and the solid surface of the tube are stronger than the cohesive intermolecular forces between water molecules. As the result of capillarity, a concave meniscus or a curved U-shaped surface forms where the liquid is in contact with vertical surface. Capillary rise in the height to which the water rises within the tube and decreases as the width of the tube increases. Capillarity is the primary force that enables the soil to retain water as well as to regulate its movement. The phenomenon of capillarity also occurs in the soil, in the same way of that water moves upward through a tube against the force of gravity. Water moves upwards through soil pores or the spaces between soil particles. The height to which the water rises is dependent upon pore size. As a result, the smaller the soil pores, the higher the capillary rise. Finely textured soils have a greater ability to hold and retain water in the soil in the inner particle spaces. We refer to the pores between small clay particles as micropores. In contrast, the larger the pore spacing between larger particles, such as sand, are called macropores. In addition to water retention, capillarity in soil also enables the upward and horizontal movement of water within the soil profile, as opposed to downward movement caused by gravity. This upward and horizontal movement occurs when the lower soil layers have more moisture than the upper soil layers, and is important because it may be absorbed by roots. Since water is held within the pores of the soil, the water holding capacity depends on capillary action and the size of the pores that exist between soil particles. Sandy soils have large particles and large pores. However, the large pores do not have a great ability to hold water. As a result, sandy soils drain excessively. On the other hand, clay soils have small particles and small pores. Since small pores have a greater ability to hold water, clay soils tend to have high water holding capacity. Waterlogging. The micropores in the soil are full of water, and the macropores allow for the movement of oxygen. The macropores fill with water, and the soil is depleted of oxygen. Denitrification. Nitrogen breaks down and is lost as a gas. The physical properties of soils affecting soil water. The components which make up the mineral-based soil include inorganic particles or minerals, organic matter, living organisms, and water and air. In figure 4, this is the composition of a loam surface soil when conditions are good for plant growth. As we can see, mineral is 45%, the air is 20 to 30%, also the water is 20 to 30%, and the organic is about 5%.
Each soil has a different types of arrangement of these components, which creates unique soil properties or soil types. Soil properties affect plant growth responses, fertilizer requirements, the soil response to management, land use capability, in example, the suitability for different land uses such as grazing versus cultivation, the drainage and water runoff, nutrient loss and leaching, and soil erosion. Soil properties such as soil structure, depth, texture, salinity, acidity, waterlogging, and compaction can limit plant growth, even when the soil has adequate nutrients. A soil properties are largely determined by its parent material and weathering during its formation. Topography, age, and agricultural practices can also affect a soil properties. Three groups of soil properties influence plant growth. Physical, or the texture and structure of the soil. chemical, which affects both the fertility of the soil and its physical properties, biological or the organism in the soil, such as bacteria, fungi, insects, and earthworm. It is the combination of these properties that determine soil health and the ability of the soil to provide ecosystem services. Soil properties influence plant growth and guide fertilizer decision making. Information relating to soil properties can be used to help guide investment decisions on farm to maximize the benefit for minimal investment. Physical properties of a soil that affects a plant's ability to grow include soil texture, which affects the soil's ability to hold onto nutrients, cation exchange capacity, and water. Texture refers to the relative distribution of the different sized particles in the soil. It is a stable property of soils and hence it used in soil classification and description. Soil structure, which affects aeration, water holding capacity, drainage, and penetration by roots and seedling. Soil structure refers to the arrangement of soil particles into aggregates or pens, and the distribution of pores in between. It is not a stable property and it's greatly influenced by the soil management practices. Soil texture is determined by the proportion of sand, silt, and clay in the soil. When they are wet, sandy soil feels gritty, silty soil feels smooth and silky, and clayey soil feels sticky and plastic, or capable of being molded. Soil with a high proportion of sand referred to as light, and those with a high proportion of clay are referred to as heavy. Soil texture classes. Sand. A soil contains at least 70% by weight of sand. Clay. A soil must contain at least 35% clay and in most cases not less than 40%. Loam. A loam soil is ideally a mixture of silt and clay particles that exhibit light and heavy properties in about equal proportion. So a soil in the loam group will start from this point and then include greater or lesser amount of sand, silt, or clay. Additional texture class names are based on these three basic groups. The basic group name always comes last in the class name. Thus, loamy sand in the sand group and sandy loam is in the loam group. Table 1 shows soil characteristic indicative of soil texture. Sand. The soil stays loose and separated and can only be accumulated in the form of a pyramid. The length of the soil ribbon is less than 15 millimeters. Sandy loam. The soil contains enough silt and clay to become sticky and can be made into a shape of a fragile ball. The length of the soil ribbon is 15 to 25 millimeters. Silty loam. Similar to the sandy loam, but the soil can be shaped by the rolling into a small, short cylinder. Soil has a silky feel. The length of the soil ribbon is 25 mm long, contains almost the same amount of sand, silt, and clay, can be rolled into 50 cm long, approximately, cylinder that breaks when bent. The length of the soil ribbon is 25 mm. Clay loam. Similar to loam, although the cylinder can bend into a U shape without forcing it, and does not break. The length of the soil ribbon is 40 to 50 millimeters. Fine clay. The soil cylinder can be made into a shape of a circle but shows some cracks. The length of the soil ribbon is 50 to 75 millimeters. Heavy clay, the soil cylinder can be shaped into a circle without showing any cracks. The length of the soil is greater than 75 millimeters. Soil structure refers to the arrangement of the particles, sand, silt, and clay, and force in the soil, and to the ability of the particles to form aggregates. Aggregates are group of the soil particles held together by the organic matter or chemical forces. Pores are the spaces in the soil. A well-structured soil forms stable aggregates, aggregates that do not fall apart easily, and has many pores of varying sizes. A poorly structured soil is either few or unstable, readily broken apart. Aggregates and few pore spaces. Storage of soil water. Rainwater can also be stored in the ground. Soil consists of particles and pores. Those pores can be filled with air but also with water. The amount of pores in a soil is different for different type of soil. The pores in clay soil account for 40 to 60% of the volume, and in fine sand this can be 20 to 45%. In soil particles have small pores in them where water can enter. Soil water. And between the particles are larger pores that can be filled. The soil is filled with water up a certain level. This level goes up and down with changing weather conditions. This water level is in the groundwater level. Infiltration is the process of water entering the soil. The picture below shows the different storage of soil water. The unsaturated soil, the saturated soil, and the flooded soil. Movement of soil water. Water movement in soil is quite simple and easy to understand in some ways, and quite complex and difficult to grasp in others. An object is free to move tends to move spontaneously from a state of a higher potential energy to one of a lower potential energy. So it is with water. A unit volume of mass of water tends to move from an area of higher potential energy to one of lower potential energy. The picture below shows the water movement in soil, the downward flow and the horizontal flow.
Direction of water movement. The total potential energy of water is the sum of the potentials from all sources. Potential energy per unit mass, per unit volume, or per unit weight is known as the potential of the water. The potential due to gravity is known as the gravitational potential, and that due to the soil particles is the metric potential. The total potential at any point is just the sum of the gravitational and metric or pressure potentials at that point. The distribution of total potential within the soil allow us to determine if water will move and the direction of movement for any soil system. If the total potentials are equal, no movement will occur. Saturated flow. This occurs when the soil pores are completely filled with water. This water moves at water potentials larger than 33 kilopascals. The saturated flow is water flow caused by a gravity's pull, while the hydraulic conductivity can be expressed mathematically as V is equals to Kf, where V is the total volume of water moved per unit time, F is the water moving force, and K is the hydraulic conductivity of soil. Saturated flow. Factors affecting movement of water. First, texture. Second, structure. Third, amount of organic matter. Fourth, the depth of soil to hard pan. Fifth, amount of water in the soil. Sixth, temperature. And lastly, pressure. vertical water flow rate through soil is given by Darcy's law. The law states that the rate of flow of liquid or flux through a porous medium is proportional to the hydraulic gradient in the direction of flow of the liquid, where it is mathematically expressed as QW is equal to negative K, open parenthesis dW close parenthesis AT over ds, where QW is the quantity of water in centimeter, and K is the rate constant, dW is the water height, A is the soil area, T is time, and ds is the soil depth. The unsaturated flow. It is a flow of water held with water potentials lower than 1/3 bar. Water will move toward the region of lower potential or towards the greater pooling force. Factors affecting the unsaturated flow. Unsaturated flow is also affected in a similar way to that of saturated flow. Amount of moisture in the soil affects the unsaturated flow. The higher the percentage of water in the moist soil, the greater is the suction gradient and the more rapid is the delivery. Water vapor movement. The internal movement is the change from the liquid to the vapor state takes place within the soil, and that is in the soil pores, while external movement is the phenomenon occurs at the land surface and the resulting vapor lost to the atmosphere by diffusion and convection. Soil conditions affecting water vapor movement. There are mainly two soil conditions that affect the water vapor movement, namely the moisture regimes and the thermal regimes. Entry of water into soil. Infiltration refers to the downward entry or movement of water into the soil surface. It is a surface characteristic and hence primarily influenced by the condition of the surface soil. Soil surface with vegetative cover has more infiltration rate than the bare soil. Warm soils absorb more water than the colder ones. Coarse surface texture, granular structure, and high organic matter content in surface soil all help to increase infiltration. The infiltration rate is comparatively lower in wet soils than dry soils. Factors affecting infiltration. First is the clay minerals, second, the soil texture, third, the soil structure, fourth, the moisture content, fifth, the vegetative cover, and last is the topography. Soil water behavior under the field of conditions. The chemical water is an integral part of the molecular structure of soil minerals. Gravitational water is held in large soil pores and rapidly drains out under the action of gravity within a day or so after rain. Capillary water is held in pores that are small enough to hold water against gravity, but not so tightly that roots cannot absorb it. When soil is saturated, all the pores are full of water, but after a day, all gravitational water drains out, leaving the soil at filled capacity. Plants then draw water out of the capillary pores, readily at first and then with greater difficulty, until no more can be withdrawn and the only water left is in the micropores. The soil is then at wilting point and without water additions, the plants die. As you can see, the picture shows the stages of water holding, the saturation, filled capacity, and the wilting point. The amount of water available to plants is therefore determined by the capillary porosity and is calculated by the difference in moisture content between filled capacity and the wilting point. This is the total available water storage of the soil. The portion of the total available moisture store, which can be extracted by plants without becoming stressed, is termed readily available water. Irrigators must have knowledge of the readily available moisture capacity so that water can be applied before plants have to expend excessive energy to extract moisture. Pore structure, low organic matter, low carbonate content, and presence of stones all reduce the moisture storage capacity of a given texture class. Clay stores large amounts of water, but because they have high wilting points, They need significant rain to be able to supply water to plants. On the other hand, sands have limited water storage capacity, but because most of it is available, plants can make use of light showers regardless of how dry they are before the shower. Plants growing in sand generally have a more dense root system to enable them to access water quickly before the sand dries out. Stages of water holding. Saturation. All pores are full of water. Gravitational water is lost. Field capacity. Available water for plant growth, while the wilting point is no more water available for plants. The picture shows below the texture, field capacity, wilting point, and available of water of different sands. Once again, we are Group 6 reporting soil water.